So let's talk about the alternating series test. Okay, so let's assume that A sub n and B sub n are non-negative sequences, so positive or 0. So then, let's see. Wait, oh my goodness, what am I doing? Sorry. Well, you don't have to erase all of it. Just erase the B sub n part. It's just A sub n is non-negative. I don't know where my brain was at the moment. Okay, so assume A sub n is non-negative. And then if, what is it? Well, non-negative could be 0. So positive is not 0, non-negative. Small detail. If A sub n is decreasing, so A sub n is decreasing, and the limit as n goes to infinity of A sub n is equal to 0, then the series n equals 1 to infinity of negative 1 to the n plus 1 times A sub n. So this is what we call an alternating series because it alternates between positive and negative. Converges. Okay, so just the, oh yeah.
How can you prove it's decreasing if it's alternating?
No, A sub n without the negative, without the alternating part. So the values, in absolute value, they're decreasing, basically. Okay, so what this says, so here if we'll prove it in a minute, but just a little note. So based off of these, you remember the harmonic series? So this series, the series 1 over n, this one diverges, right? So we showed this multiple times and we've been talking about it for a while. So that one diverges, but if I follow the alternating series test, notice that if I have the same exact series except that it's alternating, this one, notice that 1 over n, that's decreasing, right? Just going down. But then notice also that the limit as n goes to infinity of A sub n, which is 1 over n, that's going to 0. So according to the alternating series test, this series right here is going to converge, right? So the alternating portion of it makes it easier for it to converge because, and that makes sense, right? Because when you're adding up infinitely many numbers, if some of them are negative, then they cancel out some of the others, and so it should be easier to converge if you have negatives mixed in with positives, right? Does that make sense? Okay. All right. So let's talk a little bit about how this works. I'm going to show you guys a picture. Here's the idea. So notice that A sub n is decreasing. So the biggest one is A sub 1, and then all the other ones are smaller, right? And then they're alternating. And in the way we set it up here, notice that the very first term is going to be positive, right? You guys agree? Positive? Because it's negative 1 to the n plus 1. Okay. All right. So check it out. So I'm going to draw a little picture. Let's see. So let's draw a little number line. Okay, so let's say this is 0. And let's draw the partial sum. So let's say, for example, that A sub 1 is this much. So that means that if I plot the value of s sub 1, the first partial sum, so that's just equal to the first value, the first term in the sequence, and it's positive, right? So it's over here, so like let's say, for example, you can pretend that's like 10 or something. Okay, now, what do you know about a sub 2? A sub 2 has to be smaller, right? And it's also negative, right? Because it alternates, plus, minus, plus, minus, plus, minus. So that means that if you subtract it from this one, so let's say a sub 2 is, let's say it's this big, right? Because it has to be smaller. So it can't go past 0 because otherwise it would be bigger, right? So if I subtract this much from s sub 1, then that would land me over here, right? Does that make sense? So like imagine this is 10, right? So imagine a sub 1 is equal to 10. And imagine a sub 2 is equal to, let's say, 8, right? So then you have 10, and then minus 8, that lands you back over here at, what number would that be? 10 minus 8? Last time I heard that was 2. And this is the second partial sum. That's s sub 2. So that's a plus a1 minus a2. Okay, then a3 is going to be smaller than a sub 2, but that one you're going to add, right? So imagine a sub 3 looks like this. A sub 3, let's say it's this big. So it has to be less than 8, right? So let's just say a sub 3 is, I don't know, 6. So you're going to add that, though, right? So now you move over, and now you're over here. So this is the third partial sum. So that's a1 minus a2 plus a3. And then a4, now you're going to subtract, but it has to be, again, less. So do you see kind of what's happening? Because you have to go, s4 lands you somewhere over here. And then you add the next one, right? So then you go over here. And then you subtract the next one, so you go over here. And then add and subtract and add, subtract, until you land there, right? Does that make sense? Because they're alternating and each one is smaller than the other. So then it's like you're a little snake going into the little hole. Maybe not a snake, like a, like a,
What's wrong with snakes?
but they don't like wiggle like cool when they go into the hole.
Play that game on the computer and that's snake game.
I guess so. Turtles go in and then they wiggle until they get in.
Bunny turtles?
Bunnies,
Eels do that.
eels, yeah, but they don't go into holes.
Bunnies do.
Bunnies do.
But
Worms, yeah. Anyways, pick your favorite animal that goes into a hole, and that's what it looks like. But okay, a snake is okay. Okay, anyways, so that's the idea. Okay, so since we are on the ideas of that proofs are fun times, let's do some proof/fun times.
You should number your fun times.
Fun times number 2. Yeah. This is our second fun time today. Okay, so this is the idea. Okay. Get ready, warmed up, right? We're already warmed up with our proof deals. Okay, so what do we have? What do we assume? We assume a sub n is non-negative, right? All the terms of the sequence are non-negative. We assume that a sub n is decreasing, right? So that means that a sub 1 is greater than a sub 2 is greater than a sub 3, and so on and so forth, right? So a sub n is decreasing. And we also assume that the limit, as n goes to infinity, of a sub n is equal to 0. Okay, so these are our tools to prove that the series is convergent. Okay, so let's see. Okay, so this is what we're going to do. What we're going to do is we're going to start looking at we're going to break it up into pieces. We're going to look at the even partial sums. So S sub 2n. So S sub 2, S sub 4, S sub 6, and so on and so forth. Okay, so let's take a look. So let's just start writing these down. S sub 2 is equal to A1 minus A2. Yes? Okay, now since A1 is bigger than A2, then that means that S sub 2 is greater than 0. That is correct. Okay. Then S sub 4 is equal to A1 minus A2 plus A3 minus A4. Right? So just the sum of all the terms up to A4. Up to A4. Okay, now what do you notice? What is that right there? That's S2, right? So if I rewrite this as S2 plus A3 minus A4. So what do you notice about A3 minus A4? That is going to be, since A3 is bigger than A4, that piece is going to be greater than 0, right? Which means that this is adding a little bit. So if I want to compare this to S2, I would say that this S4 is greater than S2, right? Do you guys agree? Because it's S2 plus a little piece. Yes? It doesn't have to be little. It can be big. But you guys get the idea, right? So if I continue in this way, I would get that S of 2n is greater than S of 2n minus 2. Okay, so what does that mean about S of 2n? S of 2n is increasing or decreasing? It's increasing, right? Each one is bigger than the one before it. Okay, so you can already feel what we're going to use. So the partial sums are increasing. And S of 2n is bounded. What is it bounded by? What are all the partial sums bounded by? Hint, hint. It's on the picture.
10.
What's the biggest the partial sums can be? A sub 1, right? The very first term of the series, right? That's the biggest one, and then from there you always subtract and then you add, but you can never go past that initial one. So S sub 2n, all the partial sums are less than or equal to A sub 1. So
Converges.
hence S sub 2n converges by the,
Monotonics.
there we go. See, I told you that it was going to come up. Monotonic sequence theorem. Bam. Okay, so now, that was only the even partial sums. The odd ones, it's actually easier. Well, now that we have that one, we'll use it. So let's take a look at the odd partial sums. So let's see. So then the odd partial sums, what we're going to do is we're going to write them in terms of the even ones. So like, for example, if I write down S sub 2n plus 1, that's going to equal to S of 2n plus what? So notice that this looks like A1 plus A2 plus dot 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 plus a sub 2n plus a sub 2n plus 1, right? That's what the left side is. What's the right side? Or just the s sub 2n right there. That's the sum of the terms up to 2n, right? So it's basically, that is just all of this right here, right? So then what's the only thing missing? That very, very last term, right? So the only one missing is this a sub 2n plus 1. Does that make sense? So s of 2n plus 1 is equal to s of 2n plus that last odd term in the sequence. Okay, now, we already know that s of 2n converges, right? Okay, but check this out. What's the assumption that we haven't used yet? We start off with 3 assumptions. Which one have we not used so far? The last one, right? So this tells me that the limit as n goes to infinity of a sub n is equal to 0. So right here, notice that, so the limit as n goes to infinity of a sub 2n plus 1, what is that equal to? That's equal to 0, right? By that third assumption, right? So that means that s of 2n plus 1 converges to the same value as s of 2n. So they both converge to the same thing, which is what you would expect, right? It makes sense. So since the partial sums converge, then that means that the series converges, right? That's the definition. So therefore, great times the series the alternating series, -1 to the n plus 1, a sub n equals 1 to infinity, that series converges. Thumbs up? All around? Yeah. Okay, and just like before, remember, so notice that in the assumptions we have that a sub n is decreasing and the limit as n goes to infinity of a sub n is equal to 0. Here we didn't note, but we assumed that it was decreasing starting at 1. But as we know already, this means that as long as it's eventually decreasing, then it's okay, right? So we've talked about this multiple times before, that as long as there's a point where after that all the terms are decreasing, then you're still okay, right? It doesn't have to start decreasing right at the number 1. Thumbs up for that? Okay, so let's do an example.
Could you hold it down that last time, please?
Sure, I will leave it right there or so, and you can copy that while I do an example here. So let's say we want to test, let's see, what do we want to test? How about series n equals 1 to infinity of -1 to the n times n squared over n cubed plus 1. Okay. All right, so let's see. So what do we have to show? So we notice it's alternating, right? So we have to show 2 things. What are they? Has to be decreasing, eventually decreasing, and limit of the sequence without the alternating part, right? That it goes to 0. So let's do decreasing first. So how do you guys want to show that it's decreasing? Derivative. So if I look at the function x squared over x cubed plus 1, and I get the derivative, this is, so I have to use the quotient rule, right? Okay, so the denominator I have x cubed plus 1 squared, and then on the numerator I'm going to have 2x times x cubed plus 1, right? Minus x squared times 3x squared. Right? Quotient rule? Good times? So if I simplify this, notice I get, on top, I have 2x to the 4th and then minus 3x to the 4th. So that's going to equal to negative x to the 4th, right? You guys agree? And then I get 2x right there. Yes, yes? So I simplified it in one step, but that's okay, right? So the denominator is always positive, right? So this is less than 0 when 2x minus x to the 4th is less than 0, which means that x to the 4th has to be greater than 2x, right? And since we're assuming that x is greater than 0, if you divide both sides by x and then get the cube root of both sides, you get that x has to be greater than the cube root of 2. Right? So what this tells me is that as long as x is greater than the cube root of 2, then the derivative is going to be negative, which means that it's going to be decreasing. So notice that it's not decreasing from the very beginning, but after when? So this is decreasing. So this means that it's decreasing for what values of n? Well, n is a natural number, right? So they would be n greater than or equal to 2, right? Because the cube root of 2 is a little bit greater than 1. Do you have a question? Stretching. Okay. So, all right, so that's good, right? So now we need to show that the limit as n goes to infinity.
Do you round up or round down whenever you do
Up. Okay, so then the next part is the limit, right? Okay, so I find the limit as n goes to infinity of n squared over n cubed plus 1. And if I do L'Hopital's rule a couple times, I get this is equal to 0. So therefore, what does that mean? The series n equals 1 to infinity of negative 1 to the n times n squared over n cubed plus 1 converges by the alternating series test, or AST for short. Questions? Happy times?